Hi everyone. So in the yesterday's class, we had seen a few topics in the derivation from the textbook, and we had reached up to this point wherein we had derived these three formulae for one for longitudinal stress and two for the shear stresses. So in today's class, we are going to continue from here, and we are going to see how to get these formulae for the three different directions. In this particular set of equations, we just got for our x-axis. Similarly, we need to have the equations for y-axis and the z-axis. Fine. Coming to the notations, actually this is going to be called as sigma x because it is the longitudinal stress in x direction. This one we will write it as tau, and we will write it as z because it is in that particular plane, and this one here we will call it as sorry, this is going to be yx, yes, this is going to be yx, and this one is going to be tau zx. So these are the three values in x direction. We just similar to these equations, we will get for y-axis we will get sigma f x. Then we will have sigma f x, sigma y, and sigma f z. So these forces are going to be remaining the same, and the same set is going to come here with the set. What will differ is the lower one. So this will be sigma delta x. This one is going to be delta a x. Sorry, here in this case it's going to be y. Okay, this is going to be y. This is going to be y. And this is going to be y. Now, in this particular case, because this is going to be on y-axis means this one, and the area is again here, this small area, this total area actually, this is going to be ay. So because sigma fx divided by sigma ay, it's going to be shear stress. This we're going to call it as x y. Okay. This one is going to be longitudinal, so this is going to be called as sigma y, and this one is going to be called as tau z. Okay. Similarly, for this one, it's going to be delta z. The area is going to be z direction. So z, and then we have x z, z, y z. Then this one is going to be longitudinal, so it's going to be sigma z. So this will give us the components. So let's see how this is derived. So continuing from yesterday's place, we have this over here. Let's see. We know that we must use two directions to define a stress component. One direction to identify the phase on which the stress component acts, and the second direction to specify the force component from which the stress component is derived. So the stress component parallel to the surface will be called as shear stress. So that's what I was telling. So if the component is like this, the force is acting in a particular direction, and we are going to take the same area over here, then this is going to be called as the direct stress or longitudinal stress. But if the force is going to be in different direction, let's say the force here is Fy, so that's, so if we are considering this force, and if we are taking this particular area, now because the force is going to be in the same plane as the area, this one is going to be called as the shear stress, and it's going to be written as tau. So shear stress is written as tau, and the longitudinal stress is going to be written as sigma. So that's what he is calling it as shear stress, and it's going to be denoted by tau. Now the shear stress component acting on the x phase in y direction will be written as sigma tau x y. Okay, and that convention we have used earlier itself in order to find all these relations. So here the shear, the force is in y direction, but the area we are considering is in x direction. So the shear stress is going to be called as tau yx. And similarly, here the force is in z direction, but the area we are taking in is perpendicular to x direction. So the shear stress here is going to be called as tau zx. So following the similar convention, we were able to find all these relations, and that is what is being explained over here. So you can see here, sigma x is the longitudinal stress in x direction, which is defined by this limit, sigma fx by sigma delta fx by delta ax, wherein delta ax is tending towards 0. As the value reduces to 0, that's what we need to consider. Similarly, tau xy and tau xz, we have already seen that acting over here in all these situations. So let's go ahead and see what we need to do next. So moving ahead here, you can see the stress components are illustrated in figure 4.7. Here you can see the stress components are shown. It will be convenient to adopt a sign convention for the stress components. We shall again use the same convention adopted in chapter 3 and define the resulting stress components to be positive when a positively directed force component acts on a positive face. Alternatively, a positive stress component results when a negatively directed force component acts on a negative face. By consideration of action and reaction, we see that this definition follows from first. When a positively directed force component acts on a negative phase, or negatively directed force component acts on a positive phase, the resulting stress component will be negative. Okay, so this particular phase we are taking it as positive, and because this one is also acting in the positive direction, both are positive, and we end up with positive stress. That's what it is explaining. So all the stress components shown in figure 7 are positive according to this convention, because this is upwards, this is in the same direction as y component, positive y, this is in the same direction as z, and the area itself is positive. Because area itself is positive and all the forces are positive, the stresses that result from all these are also all of them going to be positive. So okay, so stress, the directions, the sign conventions used for this, we were able to. Let's see what we have in the next page. So we have here. So if we return the continuous body shown in figure 4.1, figure 4.1, 6. So again, if you want to define it, we should be able to, we should know all these components of this in order, if you want to find the stress t power n, stress vector t power n at this particular point acting in the object. So we can see that there are a total of 9 stress components. So acting on these diagonals, we can see that these are longitudinal stresses, and the remaining all stresses are shear stresses. Remaining all stresses are shear stresses. So knowing the values of all these stress components is necessary in order to find the stress vector which is acting on this arbitrary plane, the normal of which is n. So we will return to this relation between the components of this. So returning again to the continuous body shown in figure 4.1, suppose that in addition to the plane mm, so this plane that we have, this plane is called as mm. So in addition to this plane mm, we pass another plane to the body. This plane being parallel to mm, but separated from it at a small distance, delta x. If we similarly pass planes parallel to yz, xy planes, we finally cut out a parallelopiped delta x by delta y by delta z. The stress components acting on the faces of this element will be as shown in the figure 4.8, which is over here. So we are getting a parallelopiped here, which we are cutting at different angles. So I mean, this is happening in 3 dimensions. So if I want to explain it in a simple 2-dimensional body, let us say we are taking a 2-dimensional body here. We have the x direction and the y direction. So this direction being x, this direction being y. So let us say we have an arbitrary plane, the normal to which is n. In order to define all the stresses, all the stresses of this particular component, we will have to know the longitudinal x stress and the longitudinal y stress, and of course there will be so there is going to be a longitudinal stress in this direction, there is going to be a longitudinal stress in this direction, and let's say this is clockwise, this one is clockwise, this is going to be called as tau, this is x, y, this is opposite of x, y, and in order to balance it, this we will have to add the base. This is y, x, y, x, both are same. So these are the forces acting on this 2D plane. And this 2D plane, what we were able to see, Z plane has been neglected, this particular thing. So we in this particular object, when we are doing the analysis, we have to consider the Z axis also. In that particular case, this is how the 3D box is going to look like. And considering on the 2D plane, there are a total of x, y, x, y. There are three stresses acting on this particular body. So considering here, we are just going to take the positive stresses, the stresses acting on the top plane, stresses acting on the right side plane, and the stresses acting on this front plane. So when we take all these stresses, we will end up with this particular stress components. Y, right. Okay, let's say, so in figure 4.8, we assume, for example, that the stress component tau xy is uniform over the negative x space, but that when we move a distance delta x to the positive x space, the stress component in the y direction has a new value tau dash xy, which is uniform over this positive x space. Actually, the stress component in figure 4.8 should be thought of as average values for the respective phases of the point. So here we need to understand that we are taking a parallel phase at a distance of at a small distance delta x to that, and we are not just doing that, we are taking it in all the directions. So in that particular direction, in that sense, we'll have to study this slightly differently. So let's say this. Let's start with this object, and this is actually having some thickness. So, like this. Okay, So this is an object with a thickness in 2 dimensions. Okay. So this one is done in 3 dimensions. I'm just trying to explain this 3-dimensional object as 2D so that we can easily understand it. So let us assume that this is the area on which our we need to find all the stresses. So in this direction we will have stress sigma x, and so what we actually have to do here is we'll have to take this small box here, which is defined by this. So it's defined with this small box. We have to take it, and on this small box we need to find out all the stresses that are acting. On this side we have sigma x. On this side, okay, so it's like this side. So this side it's a sigma y, and then we will have stresses acting opposite. It's because of this force is delta of x. This force is delta of x. Because of this force, the stress that will act on this upper face, that's going to be tau y x. And to balance it, of course, we will need one more set of stresses, and their magnitude will also be the same. Now there are two values is taken. One on the back side is taken as the positive one, and then at a small distance, this is the small distance delta x, at which we are taking another fix. On this phase, whatever stress is acting, we will have to take as sigma x dash. Similarly, whatever is acting on the downward side is going to be sigma y, and what is acting on the upward side will take as dash. But these stresses also will have to take as dash. The positive, the downward one is tau yx, upward one is going to be tau x. Same way, on this side we will get this side whatever stress we get, shear stress we get, that is going to be with the dash. This side, whatever stress we get, will be without dash. The same thing we have to replicate it on the 3 dimensions. So when you see this particular stress, it is taken as sigma x, whereas this one, which is acting at a distance delta x on this particular face, this is taken as sigma x dash. Same way, the stress which is acting downwards, sig tau x y, this is tau xy, whereas on this distance delta x on this face, whatever shear stress is acting, that is opposite to tau xy, exactly of course, and that is taken as tau dash xy. So we have one set of values on one particular side, and on the other side we will have another set of values. Then all of these will have a dash on it. Okay. So let's see. So an alternate notation called index or indicial notation for stress is often more convenient for general discussions in elasticity. We will briefly discuss this notation here. In indicial notation, the coordinate axes x, y, and z are replaced by numbered axes x1, x2, and x3. So instead of using x, y, and z that we have used here, we will have to replace them with x1, x2, and x3. So these kind of notations will be easier to understand when we are programming it into computers. So the components of vectors such that the force delta F of figure 4.5 are then written as F1, delta F1, delta F2, delta F3, where the numerical subscripts indicate the components with respect to the numbered coordinate axis. So F1 will be acting on x1, F2 will be acting on x2, F3 will be acting on x3. So this is the convention we are using here. Now with these new conventions, what we get here, phases do not necessarily have the same magnitude since the phases are separated by small distances. In figure 4.8, we assume, for example, that the stress component tau xy is uniform over the negative x phase. Negative x phase means this is the negative x phase, and on that the tau xy, the stress that we get, we are assuming it to be uniform, and this is the negative phase. But that when we move to distance delta x, so when we move in this particular direction, the positive x phase, so this is the positive x phase. On this positive x phase, the stress component acting in y direction, so this one is written as tau xy dash, tau xy dash, which is uniform over this positive x phase. So the value tau xy and tau dash xy, they need not be same. That's what it is telling us. Actually, the stress components in figure 4.5 should be thought of as average values over the respective phases of the parallelepiped. Okay. And that average value itself we are finding by the limit. We are applying limit in order to find the average value. An alternative notation called index or indicial notation for the stress is often more convenient for general discussions in elasticity. We'll briefly discuss this notation over here. Okay, so the same thing is okay. Okay, so we had something over here. So this is what we get here. So we can therefore think of 9 components stress as simply sigma ij, where I and j take on the values 1, 2, and 3. In section 4.4 and 4.15, we shall encounter further extensions of this indicial notation. Okay. So here the I represents axis, and J is representing the force in direction. Okay. Right.